Hi, greetings and welcome back to part 2. So in the previous video we saw about the response of the three different filters and I hope you understood how these three filters work. So in this video we'll design these two circuits. I'll show you the full procedure that I follow for designing the circuits in EasyEDA, and then we'll do the PCB layout, from where you can later generate the Gerber files and make your own PCB layout, or you can be old school like me and design the circuits in this perf board. So without wasting any time, let us get started with part 2. Okay, so before designing the circuits in EasyEDA, we need to first understand how a single supply preamplifier actually works, where we were powering the preamp with something like a battery where there is only positive and negative voltage. So for understanding this circuit, we need to understand first how a split supply system works, where there is positive, negative and a common or a 0 volts. Now the audio signal that we input to our preamps or our amplifiers is AC in nature. By AC I mean at one instance it is having potential higher or the magnitude higher than the 0 volts, that is plus V, and at one instance it is having magnitude lower than the 0 volts, that is minus V. So when we power our op-amp circuits with a split supply or a dual supply system, then we are having the headroom for positive voltage and also the negative voltage. So when the audio signal is higher in magnitude than the 0 volts or the common point, it can reproduce the signal, the op-amp can reproduce the signal because it is having the plus V, higher voltage than the 0 volts, and when it's going lower in magnitude than the 0 volts, then also it can reproduce the signal because it is also having the voltage lower than the 0 volts. But for single supply, we are only left with the positive voltage and the 0 volts. So only this much headroom we are having for the op-amp. So when I am feeding this type of signal to a simple non-inverting op-amp, so if we input this audio signal into a simple non-inverting op-amp and we are powering this op-amp with a single supply, that is plus V and ground, like simple like a 12 volt battery, then what we are going to get at the output is just the positive half of the cycle. Because whenever the audio signal tries to swing to the negative half of it, then this op-amp will not be able to reproduce it because it is not having any potential lower than the ground, lower than the 0 volts. So it is just going to omit that part and it is only going to work for the positive half of the cycle. I can demonstrate this with my oscilloscope also. So let's check in that. So the setup is ready. I am inputting the sine wave from this function generator and I'm powering this op-amp circuit with a single supply or with positive and ground. So the blue line is our output from the signal generator, 10 kHz signal. Now let me power on the circuit and let's see what the op-amp outputs. So as you see, the op-amp is only outputting the positive half of the cycle and the negative half it's not able to regenerate as it's having only the positive and ground supply. So now the question is how to fix this. So in order to fix this problem, we have to fool the op-amp. We have to tell the op-amp that hey, the common point is not 0 volts now. The common point is plus V, and this plus V is basically the DC offset that we are going to add in this sine wave. So DC offset, I don't want to overcomplicate the things. Now some people get pretty much confused about this DC offset, that how can we add a DC component to a AC signal. So the DC component is nothing but we are going to shift the signal, the AC signal, to the positive half of the graph. This full sine wave, in this full sine wave, we are going to add plus V to it. So where it was 0 volts, we are going to add plus V and it becomes plus V in here. That is our 0 volts, and wherever it was plus V or the maximum peak, there we are going to add plus V again. So it becomes 2V. And wherever it was minus V, we are going to add plus V to it and it becomes 0 volts. So the full signal is shifted to plus V times. That is why the DC offset is plus V in here. And now the op-amp can reproduce the full signal because the full signal is in this positive half of it. So let us see in the circuit how we can do it. Okay, so this is the same non-inverting op-amp configuration with a gain of 2. that we used earlier. And now if we just input this audio signal here, what we are going to get as the output is just the positive half of it. And to fix this, what we do is we just add one pair of resistor and we connect it with the positive supply. This point is plus V by 2. Ideally the resistances are same, that is why it's plus V by 2. We want the resistance to be same and this to be plus V by 2. DC offset should be the midpoint of the supply voltage in here. Say this is 12 volts. So DC offset should be 6 volts. That is how we are going to get the equal halves of this. So this is 0 volts, 6 volts, this is 12 volts. This to this is 6 volts, this to this is again 6 volts. So now what we are going to get at the output in here is this signal. So let us now understand how this circuit works with a simple example. So suppose I'm inputting in here 1 volts peak to peak signal. With a gain of 2, it becomes 2 volts peak to peak signal. So what we are having or seeing is 2 volts peak to peak. If we have a DC offset of 6 volts, provided that the resistors I'm using are all of same value. So now after we add a DC offset to the signal, say this is 0 volts now and this is 6 volts. The wave is going to look like this, and when it was 1 volts, here it becomes 7 volts, and when it was minus 1 volts, it becomes 5 volts. So the signal is now swinging or riding on 6 volts. So just keep one thing in mind, that the maximum point in here is plus 12 volts because that is our supply voltage. That what we are supplying in here is plus 12 volts, 0 and 12 volts. And don't put a huge gain like some value of 10 or something, so that the signal that we are having here is going out of the range of this 12 volts, because or else then it will have a flat in here and it will have a flat in here because it becomes saturated at the points when it's not having enough voltage to reproduce the wave. So this is how the signal works. Let us see in the oscilloscope what happens. Okay, so I added this two resistors in this circuit, which is acting as a potential divider, and I have taken the midpoint and inputted into the third pin or the non-inverting pin of this op-amp, and guess what? It's now giving out the full sine wave back, and the signal that the op-amp is generating now is shifted to the positive side. So this below portion is the negative side, this upper portion is the positive side, and because of the DC offset, it's shifted to the positive side. So this is how we can actually fix the issue of using single supply for one AC signal. Okay, so now don't get too happy with this circuit because it's still having some flaws in it. If you are powering this with 12 volt battery, then no issues, this can work perfectly fine. But say if you are powering it with a transformer supply or a transformer less supply with capacitor and resistor dividers, then we are going to get into trouble, because say if the supply is having some ripple of 0.2 volts peak to peak, so that ripple we are directly introducing into the signal. You are directly introducing this ripple into the input signal. So the output what we'll get here will also have or feature this 0.2 volts peak to peak ripple, and it would sound terrible. So in order to fix this, what we are doing is we are injecting the voltage into the non-inverting input or the input signal that we are having here, and this resistor in here, it's called injection resistor. So we are not directly having the signal or the ripple into the input signal, rather we are injecting the voltage onto the input signal here. Now this setup have a simple calculation that these two resistors will be obviously the same value, and this injection resistor will have 10 times the value of this, and this capacitor ranges from 10 microfarads to 100 microfarads. In this way we can fix that ripple issue also. But it is having a lot of components in here, and there is another easy fix to all of this. So instead of non-inverting op-amp, we can use one inverting op-amp. That would fix all the issues. We can have simple the voltage divider with any ripple we want into the non-inverting input, because now we are not introducing this ripple directly onto the input signal. We are just providing the offset into the non-inverting input. Here the signal input will be coming to the inverting input instead of the non-inverting input, and the signal will be inverted. Where it's having negative slope, it will be positive slope, and where it's having positive slope, it will be having negative slope. And the gain formula also changes. It's this resistor divided by this resistor. and with a negative sign because it inverses the signal. So this is how we can simply use the single supply to a AC signal, and this is the circuit we are going to use in our preamplifier design. Enough gyan from my side. Let us go directly into the circuit making in EasyEDA. Okay, so let us start our design. So you need to open Google, then search for EasyEDA. So the website will be easyeda.com. Then in here you need to log in. I have already logged in, so you need to log in, basically create one account and then log in. Then select design online, standard edition. I never use the pro edition, so standard edition, and that's how the interface looks like. You need to create one new project, so you can create one new project in here. Say we'll name it as low pass new, save it. So this will give you the place where you can create the circuit. Now first what we need to do is we need to bring in the components that we are going to use in our circuit. So that we can do, there is one common library in here where there are some components already present, but there is one library which has almost all the components that really exists. My first component will be TLO74 and search it. Okay, now you need to search for the through hole component. Okay, so this is through hole. This is how the trace looks like for assembly components. If you have seen a circuit layout, then you will know. For through holes it will look like this. So there are 4 op-amps. We're gonna have 1, 2, 3 and 4 op-amps already in here. Next is we need a bunch of capacitor and resistors for this. So resistors, just one you can import from the library, rest all you can just copy paste. Here you can see there will be a lot of components already there. So here we're just gonna go to the section where there is resistors here, and we'll just select some resistance value. Also you can check the pitch. So the pitch, if you don't know, pitch is basically the length between the two terminals of one component. So say for here the pitch is 7.2. So this is quarter watt resistor with a pitch of 10.5. This is what we need. So I'll just have some bunch of resistors in here. We can change the values later. Now comes the capacitor. So I'm mostly gonna use the box type capacitors. Basically the main concept in here is that we can measure out the pitch of the components, and then we can directly check the pitch and import any component we want, because we can basically change the values of those. This looks good. Yep. So I will have some capacitors in here. Now what we need is 2 JST connectors for the input and output. 2 of the connectors in here. Again, you can change the connectors as per your need. And I also want one terminal block for the power supply input. This is the 2-pin. Yeah, this will work. So once we have all kinds of components ready, then we can start connecting the things. So you can zoom it in. If you press R, it will rotate. So I want it this way. This is our input. First comes is our capacitor, DC blocking capacitor. So how to connect this to components? So you just need to left click on the end of the component until you see this green line, and you have to connect it to the other component and then right click. This will connect this to components. Then you can move it around to whatever you want once it's connected. So we're going to change the value to 2.2 microfarads. That's our DC blocking capacitor in here. So this capacitor together with one resistor is going to act like a high pass filter at the starting. As I said in my first video that I want a band pass filter circuit in this design. The resistance is going to be 15k. Here I'm going to put 5. So this is 15k. Together they put a cutoff which will reduce the frequencies, or which will attenuate the frequencies below 20 Hz, and we are going to connect these 2 points, and this will be connected to the ground, main ground. So once you become used to it, you can make the circuits pretty fast. Also you can change these namings. I don't need this big name. If you remember, we are going to use one inverting amplifier in here, or we are going to use the op-amp in the inverting configuration. We need one resistance. We're going to put it here. Then we are going to connect the ends to the pin 2, and then another one is going to get connected to pin 1. Left click on the end of the component until you see the green line. Then you can have this line connected to the point you want, and then right click, it will connect, it will make a connection. So I'm going to put a gain of 3 in here, 15k in this, and another resistor in here which is going to be 5k. So together they gives out a gain of 3, minus 3 basically, obviously because the signal is going to get inverted. And here we are going to provide the voltage divider or our offset. Again we need 2 resistors. the fourth pin of TL074 is positive. We're going to create also one node. So this is the node. This we are going to mention it as VCC, and the 11th pin is ground. We can also connect this one in here. So the first op amp out of the 4 op amps is having one high pass filter in here which attenuates the signal below 20 Hz. I don't want everything to get amplified, and this adds a gain of 3, and this is our offset. So next section we are going to add the low pass filtering. Okay, so I added this 2-stage of low pass filter in here. I'm going to change the values according to my need. This is the value I have chosen. You can select any other values, and if you have seen my previous videos, there are many online calculators which you can use to calculate the cutoff frequency. So this is 2-stage of low pass filtering. I'm going to just copy the same one again to the next stage. For that, you don't need to again create all the lines. What you can do is, you can hold the control button and you can select all this and copy, Control C. So here we're going to use Control V. Okay, so that's it. That's our 4 stages of low pass filtering added. So till now I have used 3 op amps inside this 4 op amp configuration, and you can use the last op amp. I am not going to use it. You can use it to again put some gain to the circuit, but for me I don't need it, so I'm just going to delete it. And one more point, I will add one small capacitor at the feedback for the first op amp configuration also. This also acts like a low pass filter, and this will give some stability to the circuit. Okay, so this is our power supply input with a filtering capacitor and a power supply decoupling capacitor. This needs to be 0.1 microfarads. And we used a node for the positive supply here. We are going to use the same one here too. So this will automatically connect when we are laying out the PCB. This 2 points will be automatically connected once they are having the same name. And now in the output, we need a high value capacitor. This is supposed to be 10 microfarads. I need a potentiometer also in here. So that's it. That's our circuit ready. The single supply low pass filter, minus 24 dB per octave, or a 4th order with 4 stages of low pass filtering. So let us now save this. Control S. So for PCB layout, what we are going to do is we are going to select design, convert schematic to PCB. Yes, so it will ask the copper layer and all those things. I'm just gonna say apply, and it will give you the PCB board and all the components beneath like this. Okay, one thing I need to tell you, see in here, this potentiometer is not what I wanted it to be. So I need to change this component in the circuit at first. So go to the circuit. I'm gonna delete this one. I'm gonna search in the library for a 50K pot. So let's see if we get something. I guess this will work for me. This is having the 3 pins in a line, so I'll just use one relimate connector in there so I can stack it up. This is those 10-turn prim pots, small ones. You can have it in here like this. And then in the PCB, it's still not changed. So what we're going to do is we're going to say design import changes. So first it is asking me to save the changes, so I'll save it first and then design import changes. It will ask that which all things are changed and all, which just say apply changes. And yep, it has changed the component in here. So in this way you can change a lot of other things. Okay, so let us start designing the circuit. I don't actually wanted this to be in this way. Okay, so while designing the PCB layout, few things we need to make clear. Okay, so the first one is that the input, output and the power all should be in different places, not too near to one another. So U4, if you see the circuit, U4 is our power supply input. I want to place it in here. Then we have our input, signal input, which is U2. I'm gonna place it in here, say. Then we have our output, so that we're going to place somewhere near in here. Now next, what we need to do is we need to place all the components which are acting as feedback very close to the chip. So what we have in here is the C2, R2, C3 and C7, all should be close to the chip. Now see, it is having this crisscross thing in here. We can rotate it by pressing R. Now it is better. So C2 and R2 comes first. Now we are going to place all the components which are closer to one another within this boundary. I will finish this fast and then again we'll meet. Okay, so I kind of placed everything where I wanted it to be. And yeah, with up and down arrow, you can move the components too, like this. And side arrows to move it left and right, like this. So after you are happy with all the components placement, you're going to root, auto root. Only select this all layers if you are trying to do it a dual layer PCB where top layer and bottom layer both will have copper traces. For me, I only do this PCB layout in order to get help in doing the soldering for the perf board. So I only need the bottom layer. I'll uncheck this top layer and go to design rule. So now the default track width is 0.25 mil. What I normally do is I'll select it as 0.8 or 0.6, and after selecting 0.8, select this setting and say run. It will root all the traces automatically, and it says attempted 56, completed 56 and failed 0. So when it's not able to root some of the traces, it will show it in failed, and those traces you have to figure out how to root. You can use jumpers and all those things. Everything is fine, so just select OK. So yeah, our trace is all complete. This is how it looks. You can select bottom layer in here, it will only show the trace. If you select top layer, it will show the components highlighted. So now the main job comes where we need to make the star ground. And some people don't do this because you see now this is the ground. Okay, this, if you select one of the ground line, it will highlight all the others. So this is how the ground trace looks like. But you see all the ground traces are flowing over one another and to the power ground here. This is not right, and this maybe this won't produce noise for you because the traces are very small in length. The smaller the traces in length, the lesser the chance of ground loop noise happening. But when you are hooking up this in a full amplifier system, like a big amplifier system where there will be a lot of ground planes, lot of ground connections, for that place this is really a bad idea to keep the ground trace like this. Okay, so for creating the star ground, what we are going to do is, so first we have to find the place where we are going to put the star ground. Then suppose this is the ground which is getting connected to here, we don't want it, we are going to delete this line. It will show it as a normal thin line like this. So this is the track creating option here. So if you select this, it will come like this. You need to make one more change. See here, routing width, it's still 0.25 mm. What you're going to do is 0.8, and now we are good to go. So we are going to create one small line in here, and then we are going to use it like so. Okay, like this. Again, this is not needed. Similar case, this one we don't want it to get connected like this. We are going to use the track again. Select this, then here, connect this in here. So these two are already done. Similar way, this line we don't need, we delete it. We're going to select here and we are going to come up like this. So in similar way, we are going to do it for all the ground traces. And if you select one of the ground trace, like if you just hover around your cursor in one of the ground trace, it will show all the, or it will highlight all the other ground traces. So you just need to delete the lines which are connected to one another, and we're just going to have individual lines for each of the components to the ground, to the star ground here. So we'll do it for all the components and I'll come back again. Okay, so I've made all the connections to the star ground. This is very essential and people tend to avoid this. I don't know why, maybe to save some copper trays or something. Okay, once you are happy with everything, just save it. You can also view this in the 3D mode by selecting this 3D option. It will show you how your board looks like. So this is how my board looks like, and yeah, I have done one mistake about I've done two mistakes actually in this board. One is selecting this connectors, as these are not the proper JST connectors that we get. You can again update your library as I have shown, and also I have connected this backwards. This needs to be connected, or this needs to be rotated. With this 3D view, you can populate the components as per it's shown in here, and then you can lay the traces one by one by checking which pin of that particular component is connected to the which pin. And unfortunately I did not record my soldering process, but yeah, I followed the same thing. I have already created the dual supply circuit and PCB layout. I will show it to you. One more thing, you can generate the PDF file, export then PDF. You can first do it for the top layer and then you can select the bottom layer. In this way you can export the changes. You will have PDF for the traces that you have created. Similar case for the circuit also. If you go to file and export, you can export it as a PDF. It will give the circuit as a PDF, then you can print it out. And for Gerber file, you go to this PCB layout and then select fabrication, this PCB fabrication file Gerber. So now let us see the circuit for the split supply. So here is the circuit that I created for the split supply. Here I'm having two stages of gain, and at first I thought I'll be using 3 Vishay 1 microfarad capacitors, but I got a cool thing. I got the Weimar 3.3 microfarad capacitors from one local shop. So I used a single one here. Rest all things are very same. And if you go to the PCB layout of this, so this is how it looks like. Again, I created star ground in here. Here one line, it was not able to route with the auto route option, so that's why I have this line selected as a top layer. For creating the PCB, what you need to do is you need to have a jumper in here, and I have also created holes for this. And yeah, one thing I forgot to show you before is that you can also use this measure tool to measure the board width and board length for selecting the perf board or the copper clad board for this. So if I select this measure tool, left click on one of the end and then go to the other end, it will show me what is the width of this board, and it says that is 56.642 millimeters. So this is the circuit for the split supply, and I am using a 7 into 5 centimeter perf board. The red one is the Weimar capacitor 3.3 microfarad, and as you see, if I select the top layer, all the components are located exactly as it's there in the board that I have created. So this is the split supply circuit diagram. So the first capacitor and resistor section is the high pass filter section, then added the 4 stages of low pass filtering, then added another gain stage with a potentiometer, and that's the circuit for the split supply. And this is the circuit I created for the single supply with inverting op-amp configuration. This is the offset that I'm giving here with R22 and R33. The 4 stages of filtering going on here, and I added only 1 stage of gain, that is 3 in here. So this is the process that I always follow while creating my circuits. I'll first create the circuit in EasyEDA, and then I will create the PCB layout, and in between definitely I will test the circuit in the breadboard. That is the most essential part, because then only you can make changes to the circuit. So it's a lot more easier than just directly hopping into creating the circuit with just the circuit diagram. So I think this will be the end of part 2. I won't drag this video much longer. In the next video we will directly do the testing of this low pass filter boards. So that's it for today. I will see you in the next video. Till then, please do like, share and subscribe, and please press the bell icon so that you can get notified whenever I'm uploading the videos. Till then, bye bye.